So the basic problem I'll be talking about is that of gaps between square-free numbers. So I'll first introduce the problem and say some say some stuff about what one should expect in general, perhaps. So let Q1, Q2, and so forth be this sequence of square-free numbers. It's classical that square-free numbers have a positive density among the integers. And so in particular, the nth square-free number is roughly pi squared over 6 times n. So in particular, gaps between square-free numbers are on average bounded. And so one might be interested then in how large can a gap between two consecutive square-free numbers become as n goes off to infinity. And so we might desire some rate f of n for which the lim sup of the gap over f of n is finite and still positive. So if naively you might think that, okay, maybe the indicator function of the square-free numbers behaves like an IID random variable equal to 0 with probability, equal to 1 with probability 6 over pi squared and 0 otherwise. But this model turns out to be incorrect. So if you count the number of gaps of size r up to x, you can actually show that the proportion decays more rapidly than exponentially in r. So perhaps the truth is a bit smaller than log n. The best lower bound we have currently towards this question, so the, I guess, largest function we have for which this lim sup is positive is log n over log n, for which by Erdős, in which it who showed that the gaps are at least pi squared over 6 times log n over log n. And the construction just follows with the Chinese remainder theorem. So you construct some n, which is, so if n is such that n is congruent to -1 mod p1 squared, -2 mod p2 squared, and so forth for p1 through ph, the first h primes, such an n exists by the Chinese remainder theorem, and this gives you a gap of length h. And if you compute what happens, it's a gap of length log n over log n. So this has remained constant since Erdős proved it. Even the constant has stayed stationary. So Erdős suggested, without, I guess, much suggested this might be the truth. There's no good heuristic for that I know of, but it's still, whatever it is, it's close to, it seems like it's close to what the truth ought to be. For upper bounds, we're much farther. We aren't dealing in just logs. We don't even know that the exponent, that we can get gaps between square-free numbers are bounded by n to the epsilon. So I'll just be discussing exponents in this talk. So let theta star be the optimal exponent for upper bounds on the size of gaps between square-free numbers. So it's the infimum of theta for which you have an exponent of n to the theta. And so, okay, so the history of such bounds, 1/2, to my knowledge, was shown by Landau, but I might be wrong on that, just classically by Mobius inversion. In 1941, Vogels improved this to 2/5 using some methods similar to zero density estimates involving Dirichlet polynomials. Roth, with elementary methods, improved this to 1/4, and he introduced this idea of differencing, which was the basis of all future elementary methods, and combining this with some exponential sum estimates, he improved this to 3/13. Rickert with exponential sum bounds, again, improved this to 2/9. After that, for many years, there were just incremental improvements as, I guess, improved bounds were obtained for different exponential sums. And around the late 80s, early 90s, Filosetta and Trifonov in a series of papers brought back elementary methods, and this culminated in their proof of an exponent of 1/5 with purely elementary methods. And so I don't know if it's a coincidence or not, but earlier work between 87 and 92, Trifonov recovered the exponent 2/9, but with purely elementary methods. It might just be that there aren't many rationals of small height between 1/4 and 1/5, and so this is a coincidence, but or it might be that there's some correspondence between the elementary methods and exponential sum bounds, maybe a weak one. So the main result that we have is an improvement of this 1/5 exponent. So we show that for there's some delta greater than 0 for which you can get the expected asymptotic for the number of Squarefree numbers in an interval of length h with a power saving error term. So that one can get an asymptotic is not too surprising. All these previous methods would have been able to get an asymptotic with an interval length of whatever this upper bound is plus epsilon. So yeah, and also it should be possible to give an explicit value of delta. I didn't care to do so because it would be a rather poor value of delta and not a particularly meaningful one. And it should also be possible, though I haven't, there are significant details to work out. It should be possible to show that between x and x to the 1/2k plus 1 times 1 minus delta, there is a k-free number, and also that the expected asymptotic holds. And the previous best result was due to Trifonov, who got x to the 1/2k plus 1. And so the fact that this grows like a constant less than 1/2 times 1/k, so it was shown long ago by Halberstam and Roth that you can get x to the 1/2k, and this would, if this works, it would represent the first constant factor improvement. But this is not, I'm not going to focus on k-free numbers. I'll just be talking about the Squarefree methods. And if I get time around the end, I have a few slides, I'll talk about another recent result, which is related only because similar methods appear on the number of representations of an integer as a certain ternary cubic. So in this case, just the product of 3 numbers plus the sum of the same 3 numbers. So we improve on an upper bound of, we get the power saving improvement on an upper bound of n to the 1/3. N to the 1/3 was shown previously by Conry and Shah. What's important about this cubic is just that it's linear in each variable. And I'll briefly talk about why one might be interested in such a form. So it's unknown if there. Another question you can ask is what n are attainable. What n are represented by this form, apart from the number of representations. It's unknown, for example, if there are infinitely many numbers not represented by this form. And this is maybe an easier relative of the same question with quadratic terms in place of the linear terms, the Markov surface. And it has some other connections to orbits of certain matrix groups, but yeah, maybe I'll discuss more about this at the end if there is time. So now I'll discuss the reduction to a certain Squarefree sieve problem in short intervals, which which is the root to all progress on this problem. So if you expand out with Mobius inversion, the indicator function of Squarefree numbers uh, into the sum over the and sum over n in a short interval, you're reduced to showing that the for scales d between h and x to the 1/2, that the number of d in this scale which have a multiple in the short interval is little o of h. So for the purpose of getting a power saving, you have to get a power saving in the upper bound, and also you have to deal with d a bit smaller than h. That's but for our purposes, when I say little o from now on, I just mean with a power saving. So okay, and from now on, when I when I say delta, I mean d over h. This will be useful later on, and I didn't know of any better place to introduce it. And so everything from now on is going to proceed like a proof by contradiction. I'll suppose for the sake of contradiction that the size of this set of divisors is greater than h, and then I'll try to use that to get a contradiction. And so the idea that Roth had and is that if this set script d is too large, so if it were the case that x over d squared were actually less than 1, this quantity is very easy to understand. Because the nearest integer, the distance from x over d squared to the nearest integer is essentially just x over d squared. So the idea is that if d is large, we can take linear combinations of certain patterns in script d of this quantity x over d squared. And if you take a linear combination that has coefficients that aren't too large, we don't mess up this error term h over d squared, and we get a quantity that's much smaller and perhaps therefore easier to understand mod 1. And in particular, if we are able to find a linear combination that's less than 1, or say less than 1/2, then immediately we know by this, we immediately know that it's much smaller. So I'll call such linear combinations for specific pattern differencing identities. So at the moment, it seems a bit, I'll make it a bit more concrete. So the very simplest differencing identity, which I guess is what an argument of Esterman in that Roth described in his paper, and she obtains 1/4, is as follows. So if I have d and d plus a in script d, which are close together, let fdA be just the difference of x over d squared minus x over d squared, d plus a squared. So this is small for if a is small, this is smaller than x over d squared. So, and one can fairly precisely describe it, just Taylor expanding, say. So we can use this to bound the size of script d in the following fashion. So I guess so there exists by pigeon. Let's say that the size of script d is sufficiently large, nothing else about it. Then by pigeonhole, there exists some a which is in size at most the average spacing, such that d plus a is also in this set. And okay, and you can show that it's actually so for many d by pigeonhole. And so if we just focus on the case that A is of size D over the size of A is does have the size of the average gap between elements of script D, then we obtain that the fractional part of FDA is small. And we know the size of FDA, XA over D cubed. And so either this fractional part is bigger than 1, or it's the case that it's bigger than some constant, or it's at most H over D squared. You can rule out the second case. Let's maybe also, let's suppose for the sake of contradiction, this is at least H. If you rearrange this, if as long as H is smaller than x to the 1/2, you can rule out this the second case. So we have the first case, and in the first case, if you rearrange, it implies that you obtain an upper bound of x over d squared, which is sufficient as long as H is at least x to the 1/3 plus epsilon. And with a bit more care, you can just show an upper bound of x to the 1/3. There's right. So okay. So to track progress on, I guess, for which D and H we have an appropriate bound, I'll call the pair theta beta admissible if with H equal to x to the theta and D equal to x to the beta, one has a power saving upper bound on the size of script D. So in reality, it's just sufficient to save a little more than a log, but yeah. And so if you want to show an upper bound of theta naught on theta star, it's sufficient to show that theta beta is admissible for theta greater than theta naught. And so, if theta is greater than or equal to beta, that's dealt with from the start. That's not an issue. And what this estimate, the fact of, so what this shows that is that theta beta is admissible as long as 2 beta plus theta is at least 1. And so in particular, this whole region is admissible, and you can see that 1/3 is where this stops, and there's a single critical point where theta and beta are both 1/3, where if you can get an improvement, one can improve the exponent further. And so in Roth's work, in which he gets the exponent 1/4, he considered the following identity, the following differencing identity. So he allows these coefficients to take on some size. This gives you a few extra degrees of freedom, which allows you to kill more terms than this allows you to kill 3 terms in the Taylor expansion, but there's the sacrifice of multiplication by D. And so I guess Esterman had something of size XA over D cubed. Roth gets something of size XA cubed over D to the 4, which for A small is better. To use this and to get an upper bound on the size of script D is a bit trickier. So I won't go into it right now. But the basic idea is the same. As long as if RDA, say A is of size at most, say, let's suppose that A is of size delta, then RDA has size x over h to the 4 delta. And if this is sufficiently small, then that immediately implies that RDA is actually at most 1 over delta. RDA itself is at most 1 over delta. And if you consider several such D's, so you take, say, D plus A prime, that this is enough to get a contradiction. I think this argument is due to Nair, as far as I understand. But Roth had a slightly different argument. But underneath Roth's argument is this differencing identity. So what this gives us is the following new region, which is admissible. We're able to, this whole green region suddenly is, and we get a new exponent 1/4. And again, we have a single critical point. As long as we can get an improvement at when D and H are both 1/4, we're good. So now I'll give Filosetta and Trifonov's argument reinterpreted a bit. So this is their proof that theta star is at most 1/5. So let lowercase rda be the integer nearest RDA. So in particular, RDA is equal to uppercase RDA plus big O1 over delta. And let script D sub A be D for which D and D plus A are consecutive elements of script D. So in between D and D plus A, the only two elements in script D are D and D plus A. And by pigeonhole, you can show that so the D sub A are disjoint because of this non-consecutiveness condition. And you can show that their union for A at most delta, the average gap size, in the case that D has size H, is at most, you can show that these cover a positive proportion of elements of script D. So and from now on, we'll, I guess, as we have been, just recall that the size of D we're supposing is at least H, and we want a contradiction. And just for simplicity, we'll only discuss the generic case where A has size delta. This is not, it's not always clear that this is sufficient. There are cases where thought is required to deal with smaller A. But in general, if A is, the smaller A is, the more structured, And if A has size delta, then D sub A must be delta spaced because D and D plus A have to be consecutive elements, and this would fail if you had a gap of size smaller than A. So Filosetta and Trifonov's argument amounts to showing that if you fix A, the map from D to RDA is injective for D in this set D sub A. And this injectivity, so the desired bound follows so long, you get a bound on script D of delta, the number of possible A's, times the size of H. Times the size of R, which is X over H to the 4 delta. So you get a bound of X over H to the 4. Remember, we suppose that the size of D was actually at least H, and so we get a contradiction if H is bigger than X to the 1/5. And so we previously had that D sub A was delta spaced. What Filosetta and Trifonov show with another differencing identity is that D sub A is actually delta to the 4/3 spaced. And after you have that, it's delta to the 4/3 spaced. So anything bigger than delta, that it immediately follows that it's delta squared spaced. And the spacing, so there's a differencing identity that if you have such a pattern, so D is a sort of parallelogram, then right, yeah, if you have such a parallelogram, then if you can show that if B is too small and A has size delta, then one gets a contradiction in a similar fashion to earlier arguments. So, okay, so we have this new admissible region. We've dealt with all, no matter what D is, so long as H is at least X to the 1/5, we've dealt with this, exactly that and nothing more. So if we want to improve on H to the 1/5, if we want to improve on X to the 1/5, we have to get an improvement at all points along this along this flat region. So improving for when D is near H, one can use exponential sum estimates. There are also iterations of differencing identities that can always deal with H near D. And there are other arguments which can deal with H when D is near X to the 2/5 and H is X to the 1/5. So it's really these middle regions that turn out to be a challenge. So some remarks on the argument of Filosetta and Trifonov, and I guess this type of argument involving injectivity. So if we let little fdA be the integer closest to this first difference that we considered, you can also show a bit more easily that this map D to fdA is injective. And this immediately gives you the exponent 1/4. And what these arguments really amount to is just considering differencing identities for this sort of pattern that I discussed before. In this case, the differencing identity is just you consider the first difference between D and D plus A, and then you take the difference of that difference with the difference by B. So and it's in this form that Filosetta and Trifonov's argument is presented in when they get 1/5. So what they do is they consider this Roth difference and take the difference of that with the and subtract from that the same difference but translated by B. And in order for that argument to succeed, you need B to be at least delta. On average, B is delta squared. You need B to be bigger than delta, and that's what they show. But it's nicely expressed through this injectivity. So the idea we have is to actually exploit the structure that this the injectivity of this map implies. So I'll focus on the critical case H equal to X to the 1/5, and I'll suppose that delta has a bit of size. You can always deal with small delta, and certainly you can deal with delta of size H to the 1/10. And the adversarial scenario that we want to rule out is that for a positive proportion of A of size delta and R of size H over delta, there exists some D for which RDA is equal to R. And we'll call this D of RA. And what we're going to try to do is estimate D of RA and use that structure to say a bit more. And yeah, so in this case, for a you can pigeonhole a bit more, and you can say that for a positive proportion of A, there's some subset of positive density script R sub A for which I guess I didn't write it, for which RDA is equal to R for all R and for all R in R sub A. So, okay, so we know what little r, so we know that RDA is within 1 over delta of big RDA, and one can rearrange that to show that to get an estimate for D that must the D that must correspond to R and A. So in particular, it's equal to this expression, which I'm going to call D tilde of RA. And there's some lower order terms, but I'll ignore that. In this case, I think actually only the lower order terms are actually too small to matter. But yeah. So this provides us a sort of what I'll call an approximate parameterization of D, or maybe more accurately of D sub A. And we're going to exploit that. So there are 3 different ranges with, I guess, 2 or 3 different treatments. So the first regime is the most intricate, and it's elementary. It's just with differencing identities. The third is also elementary, And the second case is an extension of the third argument in which null sequences appear. So I'll discuss first these last two cases, starting with case 3. So suppose that delta is at least h to the 1/2. What we're going to try to do is use this approximate parameterization to obtain further information, about the integer near the first difference, and this will give us restrictions on R and A alone. So if we know D up to an error of multiplicative error of 1 plus big O 1 over H, then we also know F up to such an error, because little f is very close to big F. So if this error term is far superior to the error term for the Roth difference. And so if we plug that in, we obtain that f at dA is equal to f tilde at RA, where f tilde is the following monomial that we get from plugging in d tilde to f, to big F, the difference itself, plus an error of, so you can show that f has size h squared over delta squared, so f tilde, so the error here now becomes h over delta squared. And if delta is much bigger than h to the 1/2, the fact that f is an integer, this is a typo, there shouldn't be any tilde here. The fact that f is an integer implies that f tilde RA is within h over delta squared of an integer. And this is a non-trivial restriction if delta is at least h to the 1/2. And at this point, we understand f tilde sufficiently well that we can show, say, as A and R vary, that this is equidistributed mod 1. And so this can't happen for a positive proportion of R and A. And one can also proceed elementarily if you just want an upper bound. So more differencing identities would also provide the desired result. So we've dealt with all but for cases 2 and 3, we've dealt with all but the case that delta is of size h to the 1/2. So in this case, all we have is that f is equal to f tilde plus big O 1. So since f is an integer, we can actually just say that f is equal to the floor of f tilde RA up to I guess you can plus a shift by big O of 1, but I'll ignore that. It's all dealt with in the same fashion. We can feed this back into our the fact that f is very close to big F with a very good error term, and solve for D again and get a new approximation with superior error terms. So if one proceeds to solve this and say opens up, say with some Taylor expansion, you can show that dRA is equal to d double tilde RA, where d double tilde plus an error term of big O 1 over delta. You can do better than this error term. But the point is it's less than 1. It's little O of 1. Where d double tilde is the following bracket expression. And the point is that the equidistribution of such expressions mod 1 is standard now. So if you split R into, say we fix A, and we just want to show that for any given A, as you vary R, this is equidistributed mod 1, split R into short intervals and Taylor expand. So then you'll end up getting, you'll be reduced to showing that for most short intervals, the following type of bracket expression. Oh yeah, and just to be clear, this curly bracket means a fractional part. So yeah, we're reduced to showing that this is this sort of bracket expression is equidistributed mod 1 for these polynomials that are coming out of the Taylor expansion. By understanding these quantities and their derivatives, and the second derivative is mod 1, you can show that most of the linear coefficients of f1, f2, and f3 are linearly independent, mod 1. So these polynomials, if you just take f1r, f2r, f3r, they are equidistributed mod 1 by, I guess, some standard, say, Kroneker's theorem. And at this point, we note that this comes from a polynomial orbit on a certain nil manifold. So it turns out that if you take, so consider the following map to a quotient of R times the Heisenberg group, where you have F3A here, corresponding to this term, and F1A minus F2A, and so forth. And this is a polynomial map. You can show that if you keep taking commutators, this will eventually vanish. And to see how the bracket expression arises, so specifically to see how F1 of R times the fractional part of F2 of R arises, this follows by passing to a fundamental domain in which these three entries are less than or equal to 1, and you'll obtain precisely this expression. Right. So, okay. So in particular, this map to, I guess I didn't call this expression. These should be R's rather than A's. This is a typo. But
12:31.
Sorry.
Yeah, I think you can just go on.
Yes.
Everyone forgot to mute.
Yes.
Oh, right. Okay. So in particular, okay, there's a typo here, but let's say that G of R is this bracket expression we're considering here. The map from A to G of R factors through this map phi via the reduction to the fundamental domain that I described before. And so we're reduced to showing that phi itself is equidistributed on the nil manifold, rather than just showing that G of R is equidistributed mod 1. And this is what Green and Tao show with the power saving. So, so by their result, we're reduced to showing that this triple of polynomials is as I guess I should have R here rather than A. This triple of polynomials as R varies is equidistributed mod 1. So this R mod Z cubed is the abelianization of the Heisenberg group. So you just have this entry, and this entry. I guess, of course, R itself is already abelian. And this is precisely what our linear independence condition was made to imply. Okay, so now I'll go on to the case of delta much smaller than h to the 1/2. So delta, say at most h to the 1/2 minus delta, little delta. Okay, so the previous step followed by finding restrictions on individual individual values of R and A, which might appear in R sub for which R might be in R sub A. That's going to be insufficient this time. So what we're going to do is we're going to look closely at the structure of R sub A, and we're going to look closely at the structure of D sub A by looking more closely at what happens to multiple elements in R sub A. So let's say that you have 3 consecutive elements in R sub A. Maybe it's not 3 consecutive elements, but there will certainly exist, say, L1 and L2 for which R minus L1 and R minus L2 appear in R sub A many times. So let's say we have some such pattern. Let's pretend then that this happens for a positive proportion of elements of R sub A. And now consider the D's that correspond to this. So let D be D of RA, let D plus B be dr minus 1a, and D plus B prime be dr minus 2a. And just to give some context for what the scales are at this point, D is of size h delta as always. B and B prime have size delta squared, so D sub A is delta squared spaced. And we know D in terms of R and A up to an error of big O of delta. We also know B and B prime in terms of R and A up to an error of big O of delta. We can gain nothing. We're still, even though B and B prime are much smaller, we're still stuck with this resolution of delta. And by Taylor expanding, we know that B prime is actually roughly 2B, and we'll let V be this defect between coming from this error of big O of delta. And we'll use new differencing identities to obtain information about V itself. So it seems hopeless to actually obtain more information about D and B, but V, it turns out, if you obtain some information about it, suffices to give you a contradiction. So I'll give a taste of what this what goes into this, because it's quite technical to describe. But so the initial differencing identity, so the differencing identity is built out of that which Filosetta and Trifonov used to show that D sub A is more has non-trivial spacing. So you consider, for say that D and D plus B are both in D sub A, then you have then it's meaningful to consider the following differencing identity involving D plus A, D plus B, and D plus A plus B. I won't discuss these coefficients. And so this is all they use. There's also a slight correction term with this Roth differencing, which I guess I'm not going to go into enough detail about why this is important, but it's just for purely algebraic reasons involving the differencing. So of course, in this case, we know what the value of RDA and RD plus BA is up to big O 1 over delta. So this is really inconsequential, but it makes some of the algebra nicer. And so say, okay, again, recall that we had D plus B, and D plus 2B plus V. So we have that the following three values, ft of DAB, ft of DA plus DA2B plus V, and then start with the middle one. All three of these are close to an integer. So we'll consider a linear combination of these, trying to cancel out as many terms as possible in this top term, xab cubed over d to the fifth. And the differencing, so if you just, okay, you only have 2 degrees of freedom, you'll cancel the top term, and then you'll use that extra degree of freedom to cancel the next term. And the miracle that happens is that, okay, so this will have to be rearranged a little bit, but the miracle that happens is that this second term here that I've written actually cancels up to lower order terms, which can be absorbed into the error here. And so, okay, so after all this, you end up with an approximation for V, I'll call V tilde, up to an error of 1 plus delta to the fifth over h squared. So to see where that's coming from, V has size delta generically, and this error is 1 over delta plus delta to the 4 over h squared is the error occurring here. And okay, so for now fix, okay, everything we discussed now will hold for a fixed A. I'll just sketch how the argument follows without much detail. So if you now fix A and V, R must lie in an interval of length of the same relative length. I guess R has size h over delta, so this leads to an interval of length h over delta times this, which is h over delta squared times delta cubed over h. If you now use another differencing identity, so this is just the difference of two first differences. So I'll take FDA. You're trying to exploit this approximate pattern. This yields that phi sub v of r is small. It is near an integer, where phi is a certain some monomial arising from another differencing identity, which has size h over delta squared. And so you can check that as r varies, phi sub v varies by roughly 1. So it's as r varies in this interval, because we fixed a and v, we can fully understand the distribution of the fractional part of phi sub v, and this turns out to be enough to give a saving. So we've made one sacrifice by fixing v, but we can win it all back. We can win it all back via this condition, via a new differencing identity. And okay, it gets quite. So I've lied a bit here. There's a separate treatment that's needed. So this is what happens for v in the generic range. There's also another regime when v is at most delta cubed over h, and a separate treatment if v is equal to 0 has to do with lower order terms in phi sub v showing up and making this argument. And so a bit more care is required to understand the distribution of this mod 1. There's a stationary point here. This is just a monomial. In this range, the phi sub v is just a monomial. But this is the gist of the argument. And maybe I don't know if I have time to go over the proof of this upper bound for the ternary cubic. So maybe I'll just stop now, and if there are questions later, I can point to it.